Okay, good morning. David, thank you for your introduction. This is the second of a series of talks. Well, is two a series? I don't know. Anyway, the first one was about my career in the general sense. This one was in fact planned to be fairly technical, to do with trees and tree physiology and the stuff I've worked on. But somebody asked me, would I please talk about climate change, because they're very strongly linked. So it's a bit of a hybrid. I'm going to talk about trees and climate change. This is a very famous photograph taken from Apollo 12 by an astronaut. It appears all over the place, and it's called, or various things, but one of them is small blue marble. That's us, floating around in space. And it looks quite peaceful, and you think it's peaceful, but actually, unfortunately, it's not, both for human and physical reasons. The globe is rotating at, I think I have the number right, 1,674 kilometers per hour, all the time. And it rotates around the sun and gradually changes its angle over the years. And there's a constant flow of air, as we know, huge masses of air flow across the globe. They flow over mountains and get disturbed, and you get a lot of turbulence. You've got huge masses of water in the oceans and constant movement. And historically, it's not been a very peaceful. Yep. So there has historically been actually a great deal of climate change, but we are currently living in an era which for some reason is called the Holocene. And for about 10,000 years, climate has been relatively stable. And it's interesting that 10,000 years covers essentially the whole period of human recorded development, not of human evolution, but recorded development. Humans evolved around about 2 to 2.5 million years ago, and wandered around in little bands, and we struggled to know much about what went on for most of the time. But around about 8,000 years ago, we started to develop a history which left traces, and writing began, and history, as we know it, started to happen. So our main knowledge of our own race doesn't go back beyond the 10,000 years. It's less than that, which actually is not very long when you think that the Earth is 4.6 billion years ago. It's just a blink of an eye. And one of the questions, of course, is whether we're going to be able to keep it going much longer than that, because we're doing our best to mess it up. We are currently causing the climate on Earth to change independent of the things that have always caused it to change, like wax by asteroids and earthquakes and volcanoes, which spew a lot of dust into the atmosphere and change the way in which energy is received by the globe, and the way in which energy is dissipated. So there's always been these changes, but we're changing it now by changing, I can't move because of the video, that little grey band, which you see circling the globe with a little sort of hump of red on it. I should have a pointer. Have we got a pointer? No. Yeah.
Do you want me? I'll point it out for you, Joe. If you like. We're talking about here, is it?
Higher up, David.
Oh.
Joe, do you want a walking stick?
Yeah, lend me Bert's walking stick.
Okay.
Yeah.
Hang on, Bert. Forget. Thank you, Bert.
Don't forget to bring it back.
Thank you, an elegant pointer.
Hey.
Energy comes down from the sun, hits the earth, and is reflected, and also goes back as heat radiation, which is different from solar radiation. But over the last 10,000 years or so, it's been in balance, so the climates have been relatively stable. But in recent years, we have changed things by changing this band here, by pouring into it huge masses of gas, mainly CO2, but also nitrous oxide and methane. And those masses of gas are intercepting energy and altering what we call the energy balance of the Earth. So instead of the Earth receiving energy, warming up a bit and then cooling down, it's now receiving energy, warming up and not cooling down much. So what's happening is that if we go back 400,000 years or thereabouts, and these are quite good data, you might not think so, but we have amazing techniques nowadays, including ice cores from the Antarctic which go down, where they've managed to get the cores a meter long, a kilometer rather, and apparently it's a big trick to drill a kilometer and get the ice cores out. Ice cores also from Greenland, and there are a multitude of very clever scientific methods of tracking the age of things and the way things have changed, which I don't know off the top of my head in any way, it's too complicated. But these are fairly good data for carbon dioxide in the atmosphere. And you will notice that it's trotted along below this 300 level until we reach our times. And as I said, I think last time in answer to a question, when I started my career 40 years ago, or whatever it was, atmospheric CO2 concentration was about 280 parts per million by volume. It's now over 400, and that's intercepting a lot of energy and causing us a lot of problems. The temperature tracks CO2 because CO2 is a good absorber of what we call long-wave radiation. And if you keep pushing CO2 into the atmosphere, more and more energy is trapped, and gradually things increase, get warmer. This is carbon dioxide going from 1970 to 2000. There was a very enterprising American who put an instrument station on top of Mauna Loa, which is the highest mountain in Hawaii. And the reason was a good trick was because it sits in the middle of the Pacific and the winds whistle around it, and you get a relatively pure reading of how much CO2 is in the atmosphere. We also have one on the northwest tip of Tasmania, set up by CSIRO, which has been running it since about the 70s. And there are a couple more, but basically those instruments and measurements give us a very clear idea of the amount of carbon dioxide in the atmosphere. And then you get methane, nitrous oxide, and what the CFCs, which are the things we had a concern about a few years ago because they intercept ozone. Methane is much more efficient at absorbing radiation than CO2, but fortunately methane only sits in the atmosphere for about 12 years and then it dissipates, whereas CO2 sits up there for 100 years, or hundreds of years anyway, I think. And nitrous oxide also has a much more serious warming effect, and it lasts 265 times as long as, I think that should be years. No, I beg your pardon. It has an effect 265 times that of CO2, and it lasts about 120 years in the atmosphere. So our activities, our industrial activities, our manufacturing activities, all the stuff that goes with our civilization is pushing these gases into the air and enveloping the globe in a blanket which is altering its energy balance and the temperatures that we're experiencing. And here we have what's happening. The world has been getting warmer. You will see that up until about 1920 or something, temperatures go up and down, you get hot years and cold years and what have you. But certainly from 1950s, it's just gone up steadily as the CO2 and nitrous oxide concentrations have gone up. And here is a measure of global surface temperature. And I noted here, this is an American graph. It's in degrees Fahrenheit. The Americans are very slow about getting educated. But I might also warn you, just to cheer you up, that we are expecting a pretty hot year this coming year. What are the general consequences of rising global temperature? More extreme weather events. If you heat up the air, it becomes progressively more unstable, and you get the storms and floods and droughts that we're becoming regrettably more and more familiar with. High temperatures and droughts make forests susceptible to disastrous fires. I didn't want to put up any more pictures of fires. We all lived through the 2019 fires here. We see them every year. Canada's just had a really unpleasant experience, still having it, covering the northeastern US and Canada with smoke and muck from enormous fires because the forests have dried out and are burning. Unpredictable changes in agricultural productivity, you get drought, you get floods, which makes life difficult. Loss of summer ice in the Arctic. Some years ago, Diana and I did a trip up to Svalbard, which used to be called something else. But anyway, it's an island up in the Arctic, beyond the Arctic Circle. And it used to be that area had a good, complete cover of winter ice and a pretty good cover of summer ice. There is virtually no summer ice in the Arctic Ocean nowadays, well, very little, about 20%. And the reason for that is, if you think about it, the sun shines on ice and most of it is reflected, about 90%. If the ice is not there, it shines onto dark water and a very high proportion of the energy is absorbed. You might think, well, the sunshine is not very strong up in that part of the world, but integrated over the summer, there's a lot of energy goes in and it's warming the Arctic Ocean, and that not only is changing climate, but it's changing the flow of currents. Melting glaciers have got to be one of the more unpleasant problems that we're looking at around the world today. Almost all, in fact, I think all the glaciers in the world there might be one in Chile somewhere, which is not retreating, but most of them are retreating and some of them are gone. And if you live in a place like Chile, where your water supply actually depends on glaciers, this is a big problem. And it's going to be a big problem when the glaciers in the Himalayas really start to disappear, and they feed the headwaters of these massive rivers like the Mekong and the Yellow River, upon which millions of people depend in all sorts of ways. So there are some very ugly problems developing from melting glaciers. And rising sea levels, which are caused by the inflow of fresh water from melting snow and ice in Greenland and Antarctic, and thermal expansion of the oceans. we never worry much about rising sea levels. It seems like it's very slow, and it is quite slow. It's not going to bother anyone in this room. but it is a problem. And if you think back, Australia, actually, the whole area from the inlet, from Port Augusta and the lower part of the Murray-Darling Basin, used to be covered in sea. And that sea has retreated, and it may well come back in the foreseeable future. And rising sea levels of only a metre or so are going to have spectacular, if catastrophic, effects on countries like Bangladesh and all sorts of places in Southeast Asia. Very large proportions of the world's population live quite close to the ocean and will be heavily affected by those rising sea levels, not to mention the fact that they're fishing the oceans out all the time. Is this microphone okay, Bruce? Is this okay?
Yeah.
Yeah, it's fine. Causes of deforestation. I hate this sort of thing with a passion. I don't know, I think that's in Brazil. But we operate on the assumption in this so-called civilization of ours that if you want to do something like, build something, we'll just knock down what's there, flatten it, level it, get big machines, and on we go. If you take a drive from here to Geelong, you will drive through quite a long period of sort of not quite McMansions, but standard Australian bungalows, which have been built on land which is nearly floodplain. And those, if you think about it, they alter the environment of that area, because sunshine coming onto especially black roofs makes the whole area hotter. Drainage has changed. We do away with natural drainage. We run the water into artificial drains and we drain it off the land, and we modify everything. It says there, the absence of dense canopy will lead to warmer temperatures and increased stress and risk of heat strokes. Dense forest canopy is the best and most efficient absorber of energy and modifier of hot and unpleasant conditions. And we are busy destroying it as fast as we can, particularly in Indonesia, where we do it in order to plant palm trees. Colin, when you next go up there, have woods. And the Amazon is famously being cleared far too fast. When Europeans got to Australia, I believe that the forest in Australia was 20 to 30% of the land, not very much, but a good fringe of forest around all along the east coast and a nice little bit on the southwest. And we have got rid of about 30% at least of that. And we still have people in the forest industries who think it's okay to chop the forest down. I mean, they're there, why not? And it's a disaster. Here's some examples from America of what climate change does in a slightly indirect way. That bottom picture is a picture of pine, I think, loblolly pine or something, I don't know what it's called. It's been defoliated by bark beetle, which they go into the bark, they drill little holes, they upset the conducting system, and the foliage dies. The bark beetles are far more prevalent now because their breeding season has been shifted by increasing temperatures, and they breed earlier, and they go through a couple of cycles, and the forests are subject to much more serious attack than they used to be. They're not in balance anymore. Jack, why don't you move up a bit? She's peering. The fire on the left is a result of what happens afterwards, because those trees are now dead, covered in dead foliage, and it burns happily. This is an increase in area attacked by bark beetles with climate change in British Columbia. All those brown patches used to be green forests, and the bark beetle infestations have grown and grown, and the forest is not in a good state, and if they're not lucky, a bit later you will get the same sort of thing as you saw in the previous slide. You saw fires which destroy the forest. Could you pass me that glass of water? Thanks, Bruce. Dangerous feedback. This was a discovery made somewhere up in Siberia, and all those poor little trees, they're boreal forests, they grow very slowly, it's a very tough life. But what's happening there is that the permafrost is melting. Permafrost is the soil they sit in is generally, a lot of it's organic matter, it's peat-like stuff. And it's frozen and has been frozen for hundreds, thousands of years. But it's now melting, and as it melts, the trees are just tilting over. But that's not the big problem. The problem is that when permafrost melts and the substrate melts, you get the release of methane. And you will remember from my earlier graphs that methane is a nasty greenhouse gas, and we're getting pulses of methane out of the Siberian area and to a lesser extent out of Canada. Nothing much good seems to come out of Russia nowadays, and that certainly isn't very nice. And here I mentioned earlier the question of melting ice. I hope these enthusiastic scientists had their little zodiac not too far away, because you wouldn't catch me standing on that ice floe and making measurements, but we need the measurements. What they want to do is find out depths and rates of melting and so on. So these are feedbacks from climate change. So a little more cheerful maybe. What do you think of when you think of forests? Well, this is what we think of forests. Isn't that beautiful? You know, this is how it should be. And mostly it isn't, because we destroy it. And we plant pine plantations, which is okay. It's a business, it's a crop. You plant pine plantations. And those are Pinus radiata, not quite sure where, tumid area possibly. And I like this picture. I was on a trip to Chile, and these are podocarp forests in Chile, and they're more or less untouched, which is nice. I don't know how long they'll stay that way. And more pretty pictures. Deciduous temperate forest, autumn colours, mixed forests, and juniper woodland. And these photos by courtesy of my very good friend, Professor Richard Waring, with whom I've worked for years. And he takes nice pictures and provides them. And if I run out of if I have a problem and I haven't got the right sort of slide, I send him an email and say, Dick, I need a decent picture of this. And it turns up in the next day. So let's look at the current distribution of the world's forests. These are the main types: boreal, temperate, subtropical, and tropical. The boreal are the blue bands across northern Canada and Siberia and northern China. They're not as nice and even as it looks in the painting there. Obviously there are valleys, there are hills, there are differences in the way the forests grow, but they're the main types: boreal, temperate, which are mixed deciduous. This area in the US is actually one of the areas in the world where the forests are coming back, because when the Pilgrim Fathers, or whatever they call themselves, turned up in America back in, anyone know the date, 17 something, they cleared the land for agriculture, and then it turned out after a while that the land was much more fertile further west, and they walked away from it and started farming in the western states, and they left the eastern states, and the forest is growing back, so that's quite encouraging. This is the Amazon forest, and here are the African, and over there the tropical forests in Indonesia. There's a point to note here. We feel correctly that our forests in Australia are important, and there are a lot of them, and we should preserve them. But actually, when you look at us in the context of the globe as a whole, we are very small potatoes down there. We have a tiny little bit of forest, and it would be nice if we could protect it, but it's not going to make a big difference to climate change as a whole, but everything you do helps, and not destroying our forests would be a nice idea. Okay, now I'm going on to a bit of tree physiology, because in order to study how climate affects trees or any other system, you need to understand how the system works. So I've spent a lot of my career trying to figure out the physiology of trees and how they work. And all the trees, those boreal forests and the tropical forests and the temperate forests, the different species, the broadleaf, the deciduous, they're all driven by the same set of processes. There's nothing different. They're all driven by, they capture carbon dioxide from the air and through photosynthesis convert it into carbohydrates using energy from the sun. This is the primary fundamental biological process. Without it, we don't eat, and we're all gone quite quickly. And we don't get wood, of course. The carbohydrates are allocated to component parts of the trees, new foliage, stems, branches, and roots. Studying photosynthesis is one thing. Determining what happens to the products of photosynthesis turned out to be a lot harder, and I spent a lot of my career trying to figure that out. We did make progress, and I'll show you shortly. The interception of solar energy depends on the surface area of the leaves and the way they are exposed. So if trees have no leaves, they don't grow. And if trees are subject to serious drought, they drop their leaves, and photosynthesis goes down a lot quickly, and growth is checked. About half the carbohydrates formed by photosynthesis are lost by respiration, because growth is an energy-consuming and using process, and it produces carbon dioxide by respiration, and a whole bunch of it, or it goes down to the roots. Roots grow, water and nutrients have to be absorbed, so you have to have carbohydrates coming down from the leaves, down through the stems, into the roots. The roots grow and transmit up water and nutrients. That's the basic process. And the efficiency of the process obviously depends on the nutrient and water status of the foliage. So on any one aspect of those dot points, you can spend a large part of your career figuring it out, and many of us have done so. Here is a tree, a rather scrubby looking tree, and here is what happens. Radiant energy shines on the foliage, it produces carbohydrates, which, as I've just said, they pump down to grow roots. Respiration takes place as well and releases carbon dioxide back into the atmosphere. It's essential that they get watered. Surprise, surprise. We call that the hydrological cycle, and I'll get back to it. We like to talk in cycles, but This hydrological cycle consists of precipitation falling on trees or forests, and then what happens to the water? It doesn't just disappear. Some of it is intercepted by the leaves, some of it goes down into the soil, wets the soil, and is transpired up through, back through the leaves again, and so on. And if, of course, climate change causes drought, then the water cycle is interrupted and there is no water and no growth. Water is taken up by the roots. There's also litterfall and dead wood, which fall onto the floor and decompose. And that's quite an important component. If you think about a forest and all the stuff on the ground, it gradually rots, produces more CO2 and goes up into the air. In the days before we disturbed the system totally, that was fine. The CO2 would go into the air, might be caught again on its way up, or it might go into the atmosphere. It was okay, but things were in balance. Now they're not so much in balance. We have a range of methods. How did we study this stuff? You put a chamber, well, let's start at the foliage level. We had chambers, there are many types of these. You put the chamber over the leaves, you put an airflow through it, you know exactly how much CO2 is in the air, you know the flow rates, you measure the size of the leaves, and you figure out how much photosynthesis is going on. And there are many makes of such chambers, and there have been thousands of studies of this sort. I've been involved in some of them myself, and they're always interesting and good, nice to work with. These are German chambers, typically German, very efficient, very good job. Then you can move up from the foliage level to whole trees. And these trees, which somebody rudely said look as if they contain large condoms, shades of David's joke, are actually eucalypts on the campus of Richmond, of the University of Western Sydney in Richmond. And they have been there for some years. You get a constant flow of air pumped into the chambers, circulated round, very careful measurements, continuous measurement of CO2, of water, so you know how much CO2 has been taken up, how much photosynthesis there is, how much transpiration is going on, and so on. And when the trees get big enough, you have to take them out. And I don't know where this photo came from, so I can't acknowledge these blokes. But you actually then go, finally, you harvest them and you determine how much dry material there is and what's happening to all this stuff. So you develop the picture of gas exchange and gas absorption and its flow into and out of leaves and the way trees grow. And over the years, we have developed the ability to do that pretty well. As a final thing, you can also measure the photosynthesis and growth rates of whole canopies. You have some very sensitive equipment up here, and the air flows across the canopy, and you measure the rate of input of CO2 and the rate of output of water vapor, and you work out the balances, and you relate all that to leaves. And if you think about it, you're scaling up. You know about the leaves, you know about individual trees, you know about the canopy as a whole, and we can develop a pretty comprehensive picture of how forests grow and how productive they might be. So for many years I argued I could make better predictions of forest growth from these sort of physiological, from the physiological knowledge that we have, and that we should be able to determine and calculate forest growth on that basis, without using conventional mensuration techniques, which mean that you have a hard hat and a tape measure and you run around and you measure trees, and a few years later you come back and you do it again, and on you go. And that's how foresters have done it for 200 years. And when I came along with my colleagues with these ideas and said, you know, we could do this the other way around. We could actually learn how the system functions, and we could use that knowledge to calculate not only how fast it will grow, but what would be the consequence of disturbing it, or of anything from insect attack to thinning to any sort of management system. So for that you would need a model. And with a couple of friends, my friend Dick Waring, whom I mentioned just now, and Nicholas Coops, who was at CSIRO and is now a professor at British Columbia, we developed a model called 3PG. Why 3PG? Well, because Dick and I couldn't think of a name, and I remember he was working with me in Canberra, and we got this thing to a point where it was working quite well. I'd written the code, it was pretty crude code, but the model, you could put numbers in and you could get sensible numbers out. And so what are we going to call it? And Dick came walking down the corridor and he said, 3PG. So I thought, what are you talking about, Dick? 3PG. Physiological processes predicting growth. 3P, PPPG. Big deal. I suppose we could have thought of something more imaginative, but that's what it's called, and that's what it's been called for a long time. It consists of a set of equations that describe and link the processes involved. And given the starting process conditions, the model is driven by standard weather data, and it's a very highly successful model, astonishingly successful to my mind. That's a schematic of it. And that basically is a schematic of the picture I showed you with that scraggly tree with bits going in and out. But what you have to do is write a set of equations and put in the right numbers and have the right rates and controls in order to simulate all that. And here we have what my son-in-law calls the engine room. Now I thought you might like to just solve these equations while you watched, and you can tell me what the answers are when we finished. It's not very difficult. It only took, I don't know, a couple of years to do. But it's rather fun, this one. It's just for fun, just showing off. And there are others. This is just part of it. If you're really, anyone interested in this thing can look it up on the internet on a very good website, which is looked after by the University of British Columbia. Okay, guys, you can go now. Thank you. I said earlier that it's a remarkably successful model. Every one of those blue dots consists of a set of measurements on trees or groups of trees. They were collected over a number of years and seasons, all up and down coastal Chile. And then the guys doing the job took the 3PG model and they took global climate models, and they simulated the growth of the trees with 3PG, and they compared what they simulated with what they had measured in the field. And that pair of graphs is really quite, in scientific terms, is quite spectacular. So that's why I'm showing you. I wouldn't show you if it was a mess, but it's not. It's pretty good. This side is eucalypt, and that side is Pinus radiata, and you will notice, being highly observant, that is 500, and the same scale on the other side is 1,000, which is a bit surprising because it shows that the Pinus radiata were growing at twice the speed and double the productivity of the ukes. So, despite our much vaunted eucalypts, grown in 132 countries around the world and a wonderful tree, widely used, the rotten old pine still does pretty well. This is showing off. We got a prize for 3PG, an international prize, and as it says there, That's me, that's Mr. Marcus Wallenberg. Wallenberg is a very big Swedish foundation. I'm allowed to say that the Wallenberg Prize for Forest Science is analogous to the Nobel Prize for other sciences. So it's as near as we could get, because there isn't a Nobel Prize for Forest Science, but there is a Wallenberg Prize. And Diana and I went to Stockholm and we picked up the prize and we met the King and Queen. And there they are, on the right. And the really handsome lady on the right is Diana. And she had to buy a new dress. We can monitor what's happening to forests by using satellites, and of course satellite technology is a major thing nowadays, and this is how it works. This is a French slide, sorry about that, but I rather like it. These are polar orbiting satellites. What a polar orbiting satellite does is you put it into orbit above the pole, and it goes around like this, and the Earth goes around underneath it, and the satellite looks at a swath or swathe, how do you pronounce it? Whatever. Anyway, a swathe of the globe every 24 hours, and as the globe turns, the swathe moves so that over, I think it's every 24 hours, you get a complete picture of the globe, and it goes on and on and on. And they have wonderful cameras on them, and not just cameras, they are cameras and equipment that measure all sorts of stuff, of wave bands of this, that, and the other, and you can even measure chemistry and so on. The other kind of common satellite is what's called a geostationary, orbit geostationary. Anybody French? There. The geostationary satellites sit about 35,000 kilometers out in space. It's remarkable, isn't it? And they just sit there, and the Earth spins, and they have this sort of observing system, and as the Earth rotates, they keep photographing it. And these are just the Earth observing satellites. This says nothing about the mass of communications satellites and spy satellites and all the rest of it, about which actually play a very large part in our world today. Here is another test of this 3PG model. On the right, we ran the model and we made, based on satellite input measurements, we said, okay, what did we measure? You look at the various wave bands reflected by the satellites, and you can plug all sorts of information into the model, and we were able to calculate the leaf area. This is I think that's Vancouver Island, and here we have one, Washington State and Oregon and Canada. And on the right, you have what the satellite actually measured. On the left is what we calculated. So it's just a test to show that, yep, we did a good job, guys. Sorry, a minute. This takes a minute. The foresters probably didn't know and didn't like the fact that they were being monitored all the time, but they are. It's not very informative. The little yellow dots show you each year, bottom right, how much was being logged. Some years a lot. And how much got burnt. And I'm very, very happy to say, as you know, I'm sure, that the Victorian government has now stopped logging of natural forests. I think it was a dreadful practice, went on for far too long. The idea that you can just go in there and destroy not just the forest, but you destroy the habitats for all sorts of wonderful little creatures, which you just kill them by the thousand, by the million. You leave the land in no state for them to start again, and you contribute to extinction and the loss of all sorts of wonderful wildlife. I mentioned earlier that we're getting near the end. The hydrological cycle. This is just a diagram. Obviously, the rain comes down. The water is. What happens to the water? You have to preserve conservation of mass, as we call it. It can be intercepted by the trees. Some goes down the stem flow. Some comes as through fall. Some goes into the soil, is evaporated and taken up by the roots, and some goes to deep drainage, some is stored, some runs off, and over there is another evaporation. It's all the different components of that cycle are all affected in different ways. If you take out all the trees, you're going to get a lot more runoff, and that's exactly what we do in many places. Very thoughtlessly and without precaution. But if you think about it, it's really a balanced system. And this is the kind of thing that we do. I think that that slide on the right is it's really a very horrible. It's a horrible slide. That's the forester's idea of harvesting. What do we want to do? We want to harvest the trees, so we'll go and cut down the whole forest. We'll put a large amount of it through tippers. Some of it will be okay for timber, and then we'll let it regrow. And they claim that what regrows is replacing the forest. That is absolutely nonsense. If you do that to a forest, it will. Do you want some water, Bert? If you do that to a forest, it will take 200 years plus to get to any sort of state where it provides a habitat for wildlife, where it gets to anything like what was there before. But we have done that to large proportions of the southeast forests in this part of the world. In Tasmania, they still do it. They're very stubborn people, the Tasmanians. Drive you nuts. This, to me, is a much more sensible approach. I think this is also in Chile or Brazil. I've seen them do. This is tree farming. Now, if you want to have timber, fine. Let's do tree farming. You have seed beds, just like, whether it's carrots or little trees or whatever. As they get to a certain size, they're planted out in all these rows, and when they are big enough, maybe 20 centimeters or something, you go and plant them into new areas, and in a number of years, you get this sort of thing or that sort of thing, and eventually this. And you might be interested to know that in Brazil, it takes about 7 or 8 years for the trees to grow that tall. I was absolutely astonished the first time I went to Brazil to look at this business, to discover there was a huge company there which was harvesting 50 hectares per day. 50 hectares per day. And through processes like this, they were replacing them. So their harvest and replant cycle was 50 hectares per day. And so, not surprisingly, the Brazilians had a massive and highly successful pulp industry. I'm not sure how they're getting on at the moment. I think They got into an argument with the United States, but everyone does that. This slide is slightly out of place, but I thought I should put it in. I think most of us probably remember that. It was 1980 something. A horrible dust storm rolled over Melbourne. And the reason for that was that we had basically stripped the land in the Murray-Darling Basin of vegetation cover. Now, let me make the point that that is climate change. If you take the vegetation off, you change the way the land heats up and the way it, and if you get a windstorm, you get the earth loosened like that, and you have that horrible result. I hope that in the last 3 wet years, most of that land has recovered, but I don't know. It's called an externality, and economists are very good at ignoring externalities if it doesn't suit them. That means you do something and you make a mess. That's okay, as long as you make money, someone else pays the price for your mess. And that's a very... Here are externalities. That's floods in Brazil as a result of, on the left, as a result of stripping the hillsides of... You remember that slide I showed you earlier that had 3 labels on it, which I said was a horrible slide, showing bare area? That sort of thing has taken place in certain parts of the Amazon and Brazil. And when you get a big storm, possibly exacerbated by the effects of climate change, you get floods. And we know they had floods in Spain the other day, and there are floods all over the world now where we didn't used to have them, mainly because we have destroyed the land cover. We do not manage the land with sympathy. You really have to do that, and we don't do that. And the one on the right is in Pakistan. I don't think that was directly attributable to stripping the forests, but it was certainly attributable to poor land management over years. And we will have all seen those floods in Pakistan on the television, and those poor wretched people sitting on banks, and you wonder how on earth they're going to survive. I think they're very distressing pictures. So climate change is not only a matter of carbon emissions. We have to manage the land. We have to stop destroying forests. We have to stop covering good land with thousands of bungalow-type houses. And that's a social and a problem for politics. It's a political problem. I don't think there's enough thought going into this. I heard a thing the other day, I'm nearly finished, guys, which really upset me. There's a block of land of 132 hectares up in the Northern Territory, which is fairly scrubby forest, but old trees in it and so on. And some developer has got a license to clear it and build houses. And guess what they will do? Is they will just bulldoze it, and they will build your standard flat houses, and that land will be again destroyed, not to mention all the creatures that are destroyed with it. And my sympathy is totally with the native people, the Aboriginal people, because they will feel this is our country being destroyed. And I think that's a very sad thing to do, but we do it because the externality is the destruction, and nobody covers that cost. The development company will no doubt make a bunch of money and walk away, and the problem will be there for years. We have to restore and maintain the rivers and streams and watercourses, and we have to stop erosion wherever we can, and we have to rethink our economics. there's a little agenda for us to think about in the years remaining to us, which in some cases I hope are many, in some they might not be so much, but we do what we can. And the list goes on, and the little blue marble keeps spinning, and it will keep spinning whatever we do. It doesn't care. But it would be nice if we left it in a better state than we've put it into right now. Thank you very much.
Joe, do you want to take any questions?
I'm happy to take questions, David, if anyone wants. You must have had about enough of me. I was there for a rather long time.
Okay, Brian, just grab the microphone,
Yeah,
Joe,
sure.
so that we can pick you up.
Thank you, Joe, for the presentation
You're welcome.
and the description of the historical record with respect to greenhouse gases. Now, Second World War was enormous industrial production and industrial destruction.
Yep.
Is that discernible in the record? That's
Yes.
one question. And just corollary, if there were to be a serious nuclear exchange, what impact would that have?
What was it? Kawari. I missed the last of the question.
The corollary, if there were to be a massive nuclear exchange, what impact might that have on the greenhouse gas story?
The word is missing
There's a
something.
massive nuclear exchange.
Yeah.
Oh, sorry, nuclear.
A nuclear confrontation.
Brian, anything that we do which throws dust and rubbish into the atmosphere changes the greenhouse. There are periods in history where temperatures went down. In the 18-something or other, there was a big volcano in the Philippines or somewhere which exploded and threw dust into the atmosphere, and the dust circled around the Earth for a couple of years, and it reflects sunlight off. And that's what cooled it down. There was still, the sun kept shining, but the dust created a band of reflective material, and the Earth actually cooled down for a couple of years. But then as it settled, it picked up again. But if we get hit by a big meteorite or an asteroid or something like that, or we have big volcanoes, they will affect the climate. And the way they do it is quite predictable. Not exactly how many degrees, but it's going to happen. And if that lunatic with a bald head in Russia uses nuclear weapons, that will be one of the effects. I hope if he does, he uses little ones.
Thank you.
Yes.
Defoliants were used in the Vietnam War. How do they work, and do they kill the trees?
They work by taking the leaves off. They almost certainly kill the trees, because the trees can't grow without leaves. It depends a bit on the species and on what the defoliant was. If in a year or two new crops of leaves grow, many of the trees will recover. They will not grow as well as they were, and the forest will be radically altered. But anything where you do something like that will have a major effect. You need to. I remember hearing a talk by one of my professional colleagues years ago, and he started off saying, "Leaves grow trees." And that's the bottom line. Leaves grow trees, and if you destroy them, you wreck it.
Do they work by interfering with the photosynthesis process?
If they what?
Do they work by interfering with the process of photosynthesis?
Now, I think that the Agent Orange things just wiped them off like it's a herbicide. It's what you do when you spray 2,4-D or one of those nasty things around. You just kill the leaves, and the leaf just curls up and dies, and it doesn't function. You can also have them, as you suggest, stuff that's absorbed into the system and kills the plant. I think the Agent Orange stuff was just defoliants, so the trees had a chance. Andy.
Yeah, Joe, thank you for today. That was really enjoyed that. Joe, in the universities today, in the colleges today, are young people, is it more and more people studying conservation,
Yep.
forestry and all these things like you have been in?
When you give a talk like this, Andy, I can get depressed, and I do get depressed, because it's not a pretty story.
Yeah.
But what encourages me is that I have grandchildren, and these are not kids; these are grown young people, and they are pretty smart, and they know what the story is. And in that generation, there is enough awareness that we can't go on like this. These people who do dotty sort of protests and things, okay, fine. It's not always dignified, it's not always effective, but they care. And of course they have to care, they have to live in the world. And there is no reason for us to keep destroying. I'm getting on a hobby horse preaching here. There's no reason for us to keep destroying things, because it's easier to destroy and just to leave the mess. But I think there is hope in the young people, which cheers me up a bit. Colin.
Joe, I'm interested in the CO2 absorption of, say, the forests versus grasslands versus commercial crops such as rice. How much? Yeah, that's the question.
You mean relatively?
Yes.
It's a matter of how rice, Colin, strongly growing rice actually is a good absorber of CO2, because it's a fast growing crop, and you can't grow fast unless you absorb CO2. But probably the best system is a multi-tiered forest with the big trees on the top and the small trees, and the air flows through the system, and CO2 is absorbed by most of the system. Making direct comparisons, you really need to say, I'm looking at this system or that, A versus B or A versus C. This is the sort of thing we do, scientists do, and have been doing for a long time. You can get numbers on all of these things. As a direct comparison, basically a crop with a healthy foliage in good conditions will absorb CO2 and grow happily.
Joe, what is the significance of the green algae in the oceans, and how does that affect climate?
I don't know. The algae actually also photosynthesize. So algae do absorb CO2, and the oceans are a very good sink for CO2. But the problem is we've put so much into the air that we're changing the acidity of the oceans, and I don't know what the algae are doing, but I mean blue-green algae that you get in the waterways, they photosynthesize. It's the same process, but it may not be what we want there. This is just a...
Well, shouldn't we be doing more about the oceans? The green photosynthesis?
Yeah, we should be. Quite what is not clear. That guy owes me a beer. Just thinking. Oh yes, I saw a thing on the telly the other day, which you may have seen, which I thought was rather encouraging, that big ocean transport companies, the ones running these ginormous tankers, are beginning to look at how they can run these things without using massive amounts of fossil fuels. How we redeem the ocean from what we've already done to it, I don't know, except we should, one of the things we have to do is slightly off, is we should stop commercial fishing, or do commercial fishing in very clearly defined areas. And that's another, classic piece of economics. The fishing folk will say, oh, no. I mean, this is our living. We've got a good We catch fish here. If you look at the big boats that are being used to haul fish out of the ocean, and that has feedbacks because the fish probably eat algae. Some of them do. And if you disrupt a system which is in balance, it goes out of balance, and very often the result is unpredictable. And, yeah.
Okay, well, one more, and then we'll finish up.
I've got to compliment you on a wonderful talk.
Yeah.
I have one question.
I can't hear.
Okay, we're going to repeat that
Okay.
question. Do you think that increasing world population is a factor in climate change?
Indeed.
The question was, is the increase in the world population influencing climate change?
Yeah, I got it. Thanks, Colin. Yeah, increasing world population is certainly a factor in climate change because we have people breeding as we do, like, I won't say like rabbits, we outbreed rabbits, we outbreed anything. And we worry about, you see, all the politicians, what are we going to do about housing? What are we going to do about this, that, and the other? There are just basically too many people in the world. And I have a nasty feeling, which is not going to be tested in our lifetimes, but that never mind nuclear wars and things, the population problem will gradually be solved by some quite unpleasant means. If you look at, say, what's happening in sub-Saharan Africa, where we have thousands, millions of people sitting there in refugee camps with not enough to eat and not enough water and just waiting for what? For life to go by. Well, they will die in hordes, and of course they try and get across the Mediterranean and they die in the Mediterranean. Long answer, off I go again. Overpopulation is a major problem. The globe is overpopulated by humans. We are fortunate in that we lived in an era when we did pretty well. We didn't care about externalities and things. The wars were over, all good. Australia was producing sheep and what have you, and we are the people who have benefited from it. Our grandchildren are going to have a harder time, and I wish them well, but I don't know what the answers. I don't know what the answers are. Thank you.
Okay, thanks, Joe.
Thank you, Joe.
That's
I get a glass of wine.
just to help help ease the pain. Ease the pain. Thanks, Joe.
Thank you for your patience, folks.